So let's start. I will introduce first, say a few things about predictive brain theory and highlight the complexity of surprise. That will be the part that bridges between the two theories. And then I will, as I said, go on with integrated information theory, relating it to my geometric approach to complexity. So let's start. So you all know predictive processing, this idea of the brain as a predictive machine. You have these nice quotes from Andy Clark and Anil Seth. So he associates, Andy Clark associates the bottom-up recognition with the following words. From Helmholtz comes the key idea that sensory systems are in the tricky business of inferring sensory causes from their bodily effects. And then the top-down generation, instead, the brain tries to predict the current suite of cues from its best models of the possible causes. So you see we have this interplay between bottom-up and top-down connections. And Anil Seth likes to talk about reality, the perception of reality as a controlled hallucination. So these are very nice summaries of this theory. And as I mentioned, Thomas Metzinger and Vanja Wiese have a very nice collection of articles on this topic. And I'm not going into more details because we had a wonderful introduction by Helene on Wednesday. So I will just fix the notation on my next slide. I'm sorry, that's the next slide. So this, the predictive brain theory is always or often associated with some brain architecture and some computational models. So there have been a few suggestions here. One is, of course, the predictive coding work from 1999. And then there is the Helmholtz machine by Peter Dayan and co-workers, which is on the left-hand side. There you see this top-down and bottom-up connections represented in terms of generative and recognition networks. And an abstract version of this is formalized within the context of variational autoencoders, which is quite prominent these days and quite effective. And here's the notation that I was mentioning. So the system perceives, so we have the system, and the apple represents here the world, which is outside. And the system has a sensory input X caused by this world. And then it has an expectation of observing an X modeled in terms of a generative model, which takes an internal representation in terms of a latent state Z and has a conditional probability distribution over the X given Z. That's the formalization of an expectation of observing X. With that expectation, it's a subjective expectation. You associate the surprise, which is simply minus the logarithm of that probability of X given Z. Vanishing or low surprise means that X can be anticipated based on Z. The generative model should be trained for low mean surprise. I make a distinction between anticipation and prediction. So the model, the generative model can be used as a mechanism for generating mock signals X prime. So this is how one refers to X prime, and these days everybody is talking about generative AI, so signals are generated by the generative model. And these, in the predictive brain theory, these serve as a prediction of X. If the surprise is low, the mock signal X prime will be a good prediction of X. So here's a clear distinction between the prediction error, which is mainly formalized. So the prediction error will be an explicit comparison of X with a generated X prime, so with a prediction. The surprise approach does not require an explicit generation of a prediction X prime. So I can be surprised or not surprised. I can anticipate an event without actually predicting it actively. Then if you have a good generative model, you can actually invert it and define the so-called recognition model, and that can be used to infer the cause W of the sensory input X modeled in terms of Z. As it has been highlighted several times, you have no direct access to W. You have only access to representations of W. So the recognition model maps a sensory input to that internal representation Z of the world state. This inference process is believed to capture essential properties of perception. Okay, that's the notation. I will be using these images throughout the first part of my presentation. So now let's come to surprise. So let's have a look at various situations, how the surprise is computed. Let's consider compositional structure of the latent state, consisting of Z1 and Z2. And the surprise will be simply this one here. And this does not cause any problem, because if you simply imagine this one as being represented in terms of a neuron, then you have this, for example, in terms of this formula, all the information that you need in order to evaluate the surprise is local to that neuron. So you see it here. So you have the connection from this first latent unit to the sensor unit, and the second latent unit to the sensor unit. And you associate W1 and W2 with these two connections, and then a bias with the sensor unit, and all information is local. That's the important part. So it can be evaluated based on local information. And that breaks down, actually, if you go up one complexity level further. So if you consider a compositional structure in the sensor space, then the joint surprise, so that's what you want to compute, the surprise about the full sensory input, can be decomposed with this architecture into the surprise of the first unit and the surprise of the second unit. So now it's the sum of the two surprises. And that's still nice, because you can say the first unit is surprised about X1, and the second unit is surprised about X2. And then you take the sum, and then you have the full surprise. So the sum wouldn't be a big problem, but it gets much harder if you have intermediate layers. That's the problem I want to point out. So if you have a hidden layer, the surprise about the full sensory input has this structure. It's quite complicated. And for the system, in order to evaluate the surprise, to use it as a learning signal for the generative and recognition network, the system has to come up with an idea to evaluate this quantity, but it's quite complicated. So there's no way to do this. So let's summarize the first observation here. So the joint surprise is a quantity that depends on information distributed all over the system. So when people talk about the system predicting the sensory input, it's not really capturing the complexity of that we are dealing with here. The dependence on the non-local information is quite complex, as you see in this very tiny example here. Learning and perception requires the integration of the distributed information to a joint surprise. So you need to come up with a joint surprise, and that cannot simply be the sum. In this previous example, it's the sum of the local surprises, but in this case, it's not anymore. Let me highlight this with an example. So I know some people don't like this kind of experiments with, but let's go through that example. So let's say you are going to attend a presentation over Zoom of of somebody giving a talk on consciousness. So you know the subject is consciousness, okay? But for some reason your Zoom the sound doesn't work. You only see the image, and you see Carl Friston. So you think, okay, it's going to be consciousness. It's going to be on consciousness, the talk. Carl Friston is talking. I don't hear what he's saying, but it's not surprising me at all because Carl Friston is associated with consciousness research. Then there's person B. It might be located in a completely different place, or it might be very close to person A. Attending the same talk, but for some reason, that person B does not have access to the image, only hears the sound, okay? And let's assume for simplicity that the sound is not indicative of the person who is speaking, okay? So that person B will listen to the talk, and the subject of the talk, that person, so the speaker is talking about the phi value of IIT, integrated information theory. So the person B will then think, okay, it's a talk about consciousness theory. The subject is IIT, so there's no surprise. So both systems, both individuals are not surprised, but if you consider them as one system, that combined system has full access to the talk with video, image, and the sound. But think about it. If we see Carl Friston with full access of image and sound talking about IIT, that would be surprising, actually. Not because he doesn't like IIT, because it's not his thing. His thing is the free energy principle, active inference, dynamic causal modeling, but not IIT. So it would be surprising. So we, as let's say experts in the field, watching Carl Friston talking about IIT, would be somewhat surprised. But the system A and B together has full access to the visual information and the sound information, and it's still not surprised. So where's the problem here? The problem is that the system, as I described, is not integrating the information to a joint surprise, okay? And then the question would be, how should A and B integrate the information to be jointly surprised? What kind of interaction would it require for a group of individuals, a society, to be jointly surprised? The brain is somehow doing this kind of integration among the neurons. It is surprised in a unified manner. Without this integration, learning and perception as process of surprise minimization would not be possible. And the basic idea underlies this basic idea underlies the original intuition of IIT. So we have now various versions of IIT, but originally it started with this idea. And this is why I think that IIT, as a theory of information integration, is closely related to the predictive brain idea. So how can we overcome this problem and come up with a kind of integration? And here's the way actually Carl Friston is suggesting. So we consider the generative and the recognition network, and so that's the rough idea. Use the recognition network in conjunction with the generative network to tightly upper bound the surprise, and conditioned on the input, generate samples with the recognition network and test whether these samples can be locally anticipated by the generative network. And here it's more formally described. So you basically have this situation here. So on the left-hand side, the image, you have this top-down connections by the which correspond to the generative network, and the bottom-up connections corresponding to the recognition network. And that highlighted node there is actually receiving the input from the layer below, and then trying to anticipate, testing whether it's anticipating it. It's a kind of local surprise, but it has to be changed a bit. So you have to redefine the surprise. So you define this di of qp as some kind of Kullback-Leibler divergence. It's smaller than the actual local surprise. And that's referred to, I refer to this as local free energy. So the upper bound of the surprise is the free energy. You have to make the distinction also for input units. There you define really the free energy somewhat differently. But then you have this nice inequality here. So, this nice inequality, the overall surprise of the system, about the sensory input, is upper bounded by this sum. Again, we have a sum, which is nice, sum of local quantities that are interpreted as local free energy. And that sum can be very tight, a tight approximation of the surprise if we choose the recognition network Q appropriately. And that's the problem. Usually you don't have enough computational power in the system to choose it really exactly to get a very tight bound. But I think it's a very nice bound that serves as a mechanism for integrating surprise. So that's the, let me summarize a bit in a more high-level description. So I personally think that the generative, the recognition network, the recognition takes place in two ways. There's a reactive perception, so which basically applies the recognition network. It's highlighted on the left-hand side here. So the system gets, so the internal state is basically the outcome of the recognition network, which is implemented in the system. That's one way. But then there is also more implicit or more active way of perception. Basically testing out hypotheses. You form hypothesis in the latent space and then ask the question, is it a good explanation? That's a kind of using the top-down connections in order to implicitly implement the bottom-up network. So this is basically, I refer to this as perception as active inference. That's on the right-hand side. So, and I believe that the surprise integration is particularly relevant for the active inference part. And here's the summary with a few hypotheses. So the free energy of individual units is evaluated locally and accumulated in a linear fashion to form the global free energy. This quantity serves as an approximation of the actual surprise about the sensory input. The free energy is sent to the latent substrate via carrier, for example, neurotransmitter, that's a hypothesis, thereby informing it about the surprise level at the periphery of the system. Through this attachment, only the latent space carries perceptual content. This would be consistent with Helmholtz's concept of unconscious perceptual inference. And then finally, perception as an active process of causal inference requires information integration, which suggests a bridge between the predictive brain theory and the integrated information theory of consciousness. So this is my take on this bridge. And depending on how much time I still have.
You have like 20 minutes.
20 minutes, that's it.
Sure, 20.
20, yeah. So I'm now coming to the second part. So as I said, I did work on integrated information theory from a completely different perspective. Many years ago, I started in 2001, but not calling it integrated information. I called it complexity. And here's the idea. The general concept is to measure to what extent the whole is more than the sum of its parts. Okay? Everybody would agree that this is a good notion of complexity, but then how to formalize it? And here's my formalization. Basically, it is a tautology. Define the complexity of a system as the distance from non-complexity. How far is it from being non-complex? It sounds like a tautology, but it's actually a very fruitful idea, because it's in mathematics, it's often much easier to come up with a qualitative description of, let's say, a non-complex system than coming up with a quantity that quantifies the complexity directly. So, and here's an instantiation of this idea. Let's have a look at this image here, and just which is referring to mutual information. So I'm interpreting now mutual information as a kind of complexity within the conceptual framework that on the previous slide. So consider, so this simplex here with 4 corners, extreme points, is basically the simplex of the probability distributions on two units with two binary units. So let's say they have states 0 or 1. So you would have a global state space 0, 0, 1, 0, 0, 1, 1, 1. Okay? And these 4 states correspond to these corners here. And if you take probability distributions over 0, 0, 1, 0, 0, 1, 1, 1, you get all the probability distributions, they form a geometric object, which is this simplex here. But then you can ask which probability distributions are non-complex, which probability distributions are completely determined by probability distributions on the first unit, the first part, and probability distribution on the second unit, the second part. And these are simply the product distributions, right? You multiply those, and there's no further information in a product distribution than just the marginals. And this is shown in this two-dimensional surface here. So the product distributions form a so-called exponential family sitting in the simplex. And now you can take a probability distribution with some correlation, let's say, and measure its distance from being independent. Okay? So define dependence as distance from non-dependence. And the outcome of this is that you get mutual information as the result. So the mutual information that we know in information theory is one interpretation or one instance of the complexity that I have previously defined emerging from this tautology. So with the right definition, using the Kullberg-Leibler divergence, using information geometry here, you end up with something well known in information theory. You can apply this idea to Markov chains to include the processes. And Markov chains are conditional, basically conditional distributions. And you can define the, so now we are not dealing with simplices anymore. Markov chains or Markov transition matrices form a so-called polytope. It's not the simplex anymore, it's a polytope. But still, you can follow the same idea and develop the information geometry for that setting and measure the distance of a, let's say, dynamics, a Markovian dynamics, from being a collection of separated dynamics, split dynamics. And that's my definition of complexity. Here's again, here's a graphical representation of what I have just said. So let's say you consider the transition from xy to x prime, y prime. A full transition can be described in this way with this graphical model. And if you want to compare this with a split system, non-complex system, this is how I defined it. So basically, the first node has its own dynamics, and the second node has its own dynamics. And then you define a Markov kernel. You say that refer to Markov kernel as being split if it has this structure. And then you measure in the same way as we defined it previously, you measure the complexity of a global transition as distance from the set of split Markov kernels, which means distance, complexity as distance from non-complexity. And you end up with a nice measure, which turned out to be almost the same as what Giulio Tononi has defined in his original papers, which he calls the phi measure, okay? I'm not considering this issue of considering partitions of the system. I really consider only the full system and the individual units. So as I said, so it turned out what I have defined in 2001 is very similar to what Tononi has called integrated information and quantified and used the symbol phi. And this was for a long time. I kept developing my theory of complexity along these lines. And then there was a kind of revival of this connection between IIT and complexity theory by Oitsumi, who actually was working with Amari previously and in Japan, and then became a postdoc in Tononi's group. And after learning about IIT, he came back and continued working with Shunichi Amari on IIT along the lines that I have proposed previously. And they came up with with postulates for this kind of measure. They said any measure of integrated information has to be non-negative, and it has to be upper bounded by the mutual information. So there shouldn't be more integrated information or information integration than information flow in the system. So that's the postulate. And it turns out that my original measure, does not satisfy this postulate. It is non-negative, but it's not upper bounded by the mutual information. And then they came up with various ways to improve it. So the first suggestion by Amari was to add for the split system, when you go from the full system to the split system, only remove these arrows here and do not remove this undirected edge in the output. And this is because he wanted to really only capture the intrinsic integrated information, not information that is imposed on the system from outside. Okay, this is the idea of keeping this undirected edge here. And so they define what they call geometric complexity or geometric integrated information. It's the same definition, but instead of measuring we simply change the notion of a split system. So by adding this undirected edge. That's nice. And with that definition, they actually can prove, or it's easy to see, that it satisfies their postulate. But then there's a problem with it. If you want to test whether these, let's say you have this split system and you want to see if there is an edge from an arrow from y to x prime, let's say, you want to model that the absence of that arrow by saying that x prime is independent of y given x, and the absence of this arrow by saying that y prime is independent of x given y. But it turns out that for this graphical model, that's not satisfied. So that's a problem that has been observed as a problem. And this is why they changed their definition and moved on with this definition, saying, we don't know how it looks like, but we impose these two condition independent statements as the conditions for defining a split model. And we ask the question, what graphical model does this correspond to? We don't know how it looks like. So that's the final version that they have. So an implicit, instead of an explicit definition of a split model, they use an implicit version of it. And we came up with an explicit formulation of it. So by explicitly, as I said, incorporating the external world, which is basically the main motivation for having that undirected edge. But it turns out that you incorporate that world and integrate it out, you get something which is bidirected and not undirected. And that makes a difference in graphical models theory. So in graphical models theory, we then enter the field of mixed chain graphs. And so for that system, we can actually prove that the condition independent statements hold. This is what Oitsumi et al. Wanted to have. But now we have a graphical representation of that. And I think, so this, see how many minutes? Yeah, I'm done. So this is the relation of all these notions of split models and associated phi measures. This is the Venn diagram of it and their relations. I think that's all said. So here the main point is to highlight the difference between the latest version of Amari et al. And our version. So that's this difference here. And so I'm not going into the details of these plots, but I just want to finish my talk with an announcement. And I would like to thank Carlotta for all her work, who recently defended her PhD thesis. So thank you very much for all the work over the many years that we are collaborating. And I want to announce also Carlotta's talk today in Lecture Hall A. She's going to talk about integrated information in the active inference framework. Thank you very much.